So the next one is a little less intuitive, I'll say. In a perfect world, we'd have a full 3D model of a facility, and we'd run CFD, like I was saying, to simulate every little bluff body interaction and every leak's initial velocity and direction. But obviously, that's not practical. And given the limited information we typically have, especially around the exact leak mechanics at the source, the challenge is, how do we approximate these real world near field effects in a way that improves the model's fidelity to true release rates, again, without resorting to expensive techniques? So this is where the source geometry comes in. And historically, the model has always treated leaks as point sources with no initial dimensions or velocity. Kind of mathematically, they start from zero. But what we found is that modeling certain leak sources as 3D shapes, spheres or cylinders, for example, and then if we treat the emissions as actually emanating from the surface of those 3D shapes, this actually significantly improves accuracy. So what's happening is we're effectively predispersing the plume. It increases turbulence near the source. So you can see on the right, if these were tanks, you can see on the right that plume is a lot more dispersed right as it emanates from the tank. And so by the time the plume reaches the fence line, it more closely resembles a real world plume, especially in environments with a lot of strong bluff body effects near the source. So these tanks are a great example. If you've ever seen tank top emissions, they tend to have sort of a downwash effect where the emission emits from the top and then it'll roll over the side of the tank, and it creates this complex swirling and this complex 3D behavior that's nearly impossible to model explicitly. But with this volume source approach, it actually sort of mimics that impact when measured some distance away. You can actually see this visually from some work out of Dort Hammerling's group out of Colorado School of Mines, where they've done the CFD model of a tank top emission. And you can see on the right here what this looks like at the fence line compared to just a simple Gaussian puff or Gaussian plume model would be similar. And so that 3D geometry that we're adding, where we have the emission emanating from the entire surface of that geometry, and again, it's a 3D thing, and so we're getting that kind of that effect of the elevation as well. This ends up looking a lot more like what we're seeing in our model, again, without having to resort to the expensive techniques used. And here you can see the resulting improvement in rate estimation. So this is specifically the tank emissions on the right here. We're showing ground truth versus predictions, and that 1-to-1 line we're at 0.92 slope and an R squared of 0.86. So again, low bias, low variance. And so that's what we're after. And again, these are from elevated release points. And so that's often a question we get is how are you detecting at the fence line something that's being emitted 20, 50, 100 feet in the air? This is the complex 3D dynamics of leaks that we aren't always able to model, but you can see very clearly when we look at the model results. And bringing back this time series plot, you can see the tanks are the red items, and visually you can just see how well the model detected essentially every tank emission, which was a powerful validation of this approach.